Now I have to introduce something, which is that there's a difference between large and small sample confidence intervals, and that's to deal with this problem that you've seen before of bias. So there's a realization at the start of statistics that when you had small samples, you were being very overly optimistic based on a limited amount of data as to your estimates, and you could get them seriously wrong. So I'm going to talk about how you calculate the confidence interval for small samples of data. Now, it's not drastically different to the way that you do it for large samples of data, but the first realization is that the normal distribution is not appropriate. It's too narrow and you need a wider, different shaped, well, it's the same shape, but different spread distribution. And so we use something called the t statistic instead, the t distribution. This was invented by a person called Gossett, who was working for Guinness, and because Guinness didn't want him publishing his statistical methods because they wanted to keep it a trade secret, he published in scientific journals under the name Student. So it's sometimes called the Student's T statistic, and things related to it are the Student's T-test. Now, SPSS actually treats all samples as small samples and uses this version of the formula. It doesn't use the large sample confidence interval formula, and it doesn't take the values for the thresholds from the Z distribution. It uses these T's. So the T distribution depends on the size of your data. So it's calculated, its width depends on what's called the degrees of freedom. Now the degrees of freedom are the number of things in your sample minus 1. So if you have degree of freedom of 1, you've actually got 2 in your sample. That's the smallest sample you can have. As your degrees of freedom go beyond 30, then it approaches the normal distribution. So if you look at this carefully, you can see that the yellow distribution is very close to the dashed line. So as your degrees of freedom become larger and larger and they go towards infinity, the t distribution becomes the normal distribution. So it is symmetric like the normal, but it is broader and flatter, and it depends on the size of the sample. You can't just pick a single value like you can with the Z statistic for a particular level of confidence. You have to look up in tables using the degrees of freedom. So this is what tables would look like. So here you've got a table for the confidence level. You can see the Z statistic is the first column, so when a Z is for a 95% confidence level is 1.96. Those are the 1.96 standard deviations above and below the mean that we've talked about before. Now if you had 10 degrees of freedom, so 11 in your sample, and you wanted to do exactly the same 95% confidence interval, then the width of your confidence interval is now 2.23 standard errors of the mean rather than 1.96. As your sample gets smaller and your degrees of freedom goes down, the confidence interval gets wider, and this is reasonable. As your sample gets smaller, it becomes less representative, it's more likely to be biased, and it's harder for you to specify the confidence interval with any level of confidence. The general formula is written like this, so it's exactly the same as the Z formula. Confidence interval is the mean, so the x bar, plus or minus, so you do 2 separate calculations for each of the ends of the confidence interval, the t critical, so the number you've just found from the tables, times s, so the standard deviation of your sample, divided by square root of n. So an example here is 6 potato strips taken from the same potato and their masses weighed before and after soaking in 1 molar sodium chloride for 1 hour. This is the typical potato osmosis experiment. You measure the mean mass of the potato strips before the experiment, which was 1.93 grams. The standard deviation of the mass before the experiment was 0.07. The mean mass of the potato strips after the experiment is 1.45, and the standard deviation of the mass of the potato strips after the experiment is 0.09. What I want you to do is calculate the 95% confidence interval for the mass of the potato strips before and after the soaking experiment. So how, and also I want you to think, how would the confidence intervals have changed if the statistics were for 10 samples and not 6? If each of the samples contained 10 potato strips instead of 6. Now, the meaning of a confidence interval is often confused. People think that it contains there's a 95% chance that the confidence interval, the mean is within this confidence interval. Now that's not quite right, because if you think about that, it's like I'm saying, if the incident of an illness within a village, let's say COVID. So 95% of the people within my village have got COVID. That doesn't mean each of the individual people, 95% has COVID. It means 95% of them do have it, but 5% of people don't have it. They're yes or no's. So a confidence interval either does contain the population mean or it doesn't. So what the confidence interval is meaning is if I created 100 of them, I got 100 samples, 95 of them would contain the true mean, but 5 of them won't. Now your problem is that you never know whether you've got an accurate confidence interval. You never know if you're definitely one of the 95 or one of the 5. So here's an illustration of that problem. What I've done here is created normally distributed data with a mean of 0 and a standard deviation of probably 1 or 0.1. What you're doing here is calculating the confidence intervals. Now, first thing to point out is almost none of the circles fall on that line, fall on the 0 line. So this is saying that if I did a point estimate based on just the mean of each of my samples, most of the time the mean of the samples is not exactly the population mean. But then I've calculated the confidence intervals, which are between those two whiskers on either side. Now almost all of the confidence intervals contain that dashed line. The ones that don't are highlighted in red. So in the top box I've got 1, 2, 3, 4, 5. I've got 6 out of 100 are wrong and don't include the actual mean, the actual population mean of 0. That's slightly worse than I'd have expected, but that's the nature of probability. I ran that process again, and in the second one I've got 4 that happen to not contain the population mean. So actually, in average, between the two of them, across 200 samples, I have 10 that don't contain the population mean. So that's 5 in every 100. So that is the 5% where I'm getting them wrong. It's really important to bear this in mind. You cannot tell for sure that you're ever 100% accurate.